Every few years, the tropical Pacific Ocean heats up, storms shift, and coastlines flood or dry out, depending on where you live on Earth. Then, usually within a year, it fades. Geological records suggest that, once, it may not have faded at all. Buried in ancient seafloor mud and fossil shells, scientists have found a signature resembling an El Niño that lasted not for months, but for hundreds of thousands of years. If that lock happened again, it would not be contained to a handful of countries for a single season. Fisheries could collapse, monsoons could fail, and food supplies that billions of people depend on could be disrupted for decades. It has happened before at smaller scale. The El Niño of 1876 to 78, one of the strongest ever reconstructed, coincided with monsoon failures across India and China and drought across Brazil's northeast, feeding a famine that historians now estimate killed tens of millions of people across those three regions combined. It was not recognized as a single connected disaster at the time. Only in hindsight, once scientists reconstructed the ocean temperatures of those exact years, did researchers realize the droughts in three regions thousands of miles apart had shared one cause. A single strong El Niño illustrates the scale. The event of 1997 and 1998 killed an estimated 23,000 people and cost the global economy tens of billions of dollars. One economic analysis of El Niño events since 1982 estimated that a single strong event cost the world economy several trillion dollars in lost income over the 5 years that follow, spread across nearly every country on Earth. Indonesian and Malaysian forests burned for months that year, blanketing Southeast Asia in smoke so thick that airports closed and hospitals filled with respiratory patients. Peru's coastal deserts, some of the driest places on the planet, turned into flash flood zones, washing away roads, bridges, and entire neighborhoods built on dry riverbeds. All of that came from an event that lasted around 1 year before the ocean cooled and reset. A version of the ocean that never reset would extend those same conditions indefinitely. El Niño begins in the equatorial Pacific, where trade winds normally push warm surface water westward toward Asia and Australia, leaving cooler water to well up along South America's coast. That wind pattern is part of a larger loop of rising and sinking air called the Walker Circulation, named after the British scientist who first described it in the early 20th century while studying failed Indian monsoons. When those winds weaken, the warm water sloshes back east instead, piling up off Peru and Ecuador. Fishermen there noticed it centuries ago, often arriving around Christmas, and named it after the Christ child. The feedback loop behind it was mapped over the following decades. Weaker winds let warm water spread east, and that warm water weakens the winds further still, each one feeding the other until the whole system tips into a full event. Normally, the ocean corrects itself within 9 to 12 months, swinging back to normal or overshooting into its cooler counterpart, La Nina, named by the same fishing communities, this time for the girl. For decades, forecasters could describe that reset without explaining what caused it. Researchers eventually traced the explanation to sediment cores drilled from the ocean floor. Around 3 million years ago, during the Pliocene epoch, carbon dioxide levels in the atmosphere sat close to where they are today, yet global temperatures ran several degrees warmer than now. Global sea levels during the Pliocene are estimated to have stood roughly 5 to 25 meters higher than today, a difference tied to smaller ice sheets on Greenland and Antarctica. Scientists reconstructed that ancient ocean by analyzing fossilized plankton shells preserved in seafloor sediment cores, a chemical record of the water temperatures those organisms once lived in. One especially detailed core, pulled from Sediment Ridge near the Galapagos Islands, captured the ancient Pacific's temperature pattern in unusual detail. The normal temperature difference between the warm western Pacific and the cool eastern Pacific, the mechanism that drives El Niño's on-off cycle, appeared almost flattened out. Researchers who first identified that flattened signal gave it a name that has stuck in the field ever since: the permanent El Niño. Around the same period, fossil soil and pollen records from East Africa show grasslands expanding at the expense of forest, a shift some paleoclimatologists link to the same disrupted rainfall patterns a Pacific locked in that state would have produced worldwide. In that reconstruction, the eastern Pacific off Peru stayed warm year-round, the way it normally only does during a strong El Niño winter for tens of thousands of years at a stretch. That reconstruction found rainfall patterns, droughts, and storm tracks across half the planet locked into an El Niño-like shape for geological ages, at carbon dioxide levels close to where the atmosphere sits today. The finding was published in the journal Science in 2005 and became one of the most cited data points in modern paleoclimate research. That coincidence between ancient and modern carbon dioxide levels made the permanent El Niño idea a significant subject of debate in paleoclimate science, and other researchers pushed back with climate models instead of fossil chemistry, running coupled ocean atmosphere simulations of the Pliocene Pacific. Modeling teams, including researchers at Yale University, still produced a Pacific that cycled between warm and cool phases, just faster and weaker, partly because shell chemistry itself can be distorted by factors that have nothing to do with temperature. More than a decade in, two different hypotheses remained on the table: either a single event that simply failed to switch off, or an entire climate baseline that shifted toward El Niño's rainfall pattern for those tens of thousands of years. The mechanism that ends a normal El Niño is called the recharge-discharge oscillator. Warm water builds up in the west, tips east during an event, then drains away, leaving the tropical Pacific too depleted of heat to sustain the pattern. Oceanographer Fei Jean formalized that mechanism in the 1990s, describing El Niño's rise and fall as the product of ocean waves that take months to cross the Pacific and reverse the system from within. If that discharge failed to happen, decade after decade, Peru's coastal fisheries will be first to feel it, since the cold, nutrient-rich current that feeds them depends entirely on the trade winds staying strong. The Peruvian anchoveta fishery already collapses during strong El Niño years, and it happens to be the single largest fishery on Earth by weight caught, feeding fish meal into chicken, pig, and farmed salmon feed worldwide. In 2023, Peru canceled its anchoveta fishing season outright, an emergency measure that idled tens of thousands of fishing jobs along its northern coast. Fish meal prices climbed sharply in the months that followed, a ripple that reached salmon farms in Norway and pig feed mills in China. Indonesia and Australia sit on the drought side of that same pattern. Rainy seasons shrink, peatlands dry out, and fires that would normally smolder harmlessly instead spread for weeks. During the 2015 event alone, satellite monitoring found Indonesia's peat fires releasing more daily carbon emissions than the entire United States economy on some of the worst days. Across the Indian Ocean, El Niño years are statistically linked to a weaker Indian monsoon, the seasonal rain that over 1 billion people depend on for growing rice and wheat. 6 months into 2023, none of these places had any reason to think the others were feeling the same ocean. Monsoon rainfall that year came in below normal, and by early 2024 India had restricted rice exports to protect its own food supply, a policy that pushed global rice prices to their highest level in over a decade. Deep in South America, the 2023 El Niño helped push the Amazon into its worst drought in decades, dropping the Rio Negro at Manaus to its lowest recorded water level and leaving isolated river communities stranded without boat access to food or medicine. One ordinary El Niño year had already produced a canceled fishery, a rationed grain supply, and a stranded river community across 3 continents inside 12 months. Every one of those 2023 and 2024 impacts happened during a single moderate to strong El Niño that lasted about a year. Researchers are still studying what would happen if that same event did not end on schedule. Coral reefs would face bleaching level heat as a baseline rather than a once-a-decade emergency. Reefs need 10 to 15 years to recover between severe bleaching events, yet the world already suffered 4 global bleaching events between 2014 and 2024, barely 2 years apart. Every strong El Niño year on record, including 1998 and 2016, ranks among the hottest years ever measured, and 2023 and 2024, riding that same event, became the first and second hottest years ever recorded within 12 months of each other. Even the mid-latitudes would feel a permanent version of it. El Niño winters pushed the jet stream south, the way the 2022 to 2023 atmospheric rivers soaked California and ended a decade of drought in weeks, while that same shift calms the Atlantic hurricane season and stirs up more storms off Mexico's Pacific coast instead. El Niño has broken within 1 to 2 years in every instance measured so far. The physical mechanism behind that pattern begins with heat itself. As warm water piles up in the eastern Pacific during an event, the western reservoir feeding it thins out, since there's only so much warm water to redistribute before supply runs low. Once that western reservoir depletes enough, the pressure difference across the Pacific reverses, trade winds strengthen again, and the whole system swings back, sometimes overshooting into a cold La Nina before settling. That negative feedback is built into the physics of an ocean basin with finite depth and finite heat. Most researchers cite this mechanism as the reason a single El Niño event, as defined today, cannot run indefinitely. That swing runs in both directions. An unusually long La Nina between 2020 and 2023 deepened drought across the Horn of Africa before flipping straight into the strong El Niño of 2023. The debate over what exactly happened in the Pliocene remains unresolved, but since a single event cannot physically run forever, most researchers in the permanent El Niño camp now argue the planet's entire climate baseline shifted toward El Niño's rainfall pattern for those tens of thousands of years. Some current climate models suggest continued tropical Pacific warming could push toward that same kind of baseline shift in coming centuries, while other modeling teams project a Pacific that keeps its normal on-off rhythm intact. Some recent modeling work has tried to split the difference. Projections published in the past few years suggest continued ocean warming could dampen the size of the swing between El Niño and La Nina without shutting the cycle down completely, a middle scenario between a full permanent lock and no change at all. For most of history, nobody could watch the entire Pacific Basin at once. A major El Niño in 1982 and 1983 went largely undetected until it was already devastating fisheries and rainfall worldwide, prompting governments to fund a permanent network of ocean buoys and, later, satellite monitoring across the tropical Pacific. Sea surface temperatures across the tropical Pacific have measurably risen since the 1950s, and the strongest El Niño events on record have all landed within the last 3 decades. The event that began in 2023 ranked among the strongest ever recorded and helped push global average temperature past 1.5 degrees Celsius above pre-industrial level for the first time in recorded history, if only temporarily. The World Meteorological Organization formally declared that event in July 2023, and average global ocean surface temperatures went on to set a daily record for more than a year afterward. 3 million years ago, the shells and mud of that same ocean recorded a rainfall signature that matches, by every proxy measurement taken since, the pattern expected of a world locked permanently into El Niño's rhythm. Rice and cocoa prices have both spiked during the last 2 El Niño events. Cocoa prices reached a record above $10,000 a metric ton in early 2024 after drought in Ivory Coast and Ghana, the source of most of the world's cocoa, cut harvest during that same El Niño. Robusta coffee prices tied to Vietnam's drought-hit harvest more than doubled between 2023 and 2024, the sharpest rise in over a decade. Economists Christopher Callahan and Justin Mankin at Dartmouth College published a $1 trillion estimate in the journal Science in 2023, tracing how a single El Niño drags down economic growth in countries worldwide for years after the ocean itself has calmed back down. Running their model forward, they estimated that El Niño events occurring more often and more intensely under continued warming could cost the global economy a cumulative $84 trillion by the end of this century. That $84 trillion figure assumes El Niño keeps breaking on schedule, the way it has in every measurement taken so far, and still finds its way back to some kind of normal within a year or two. The Pliocene mud still cannot say for certain whether that ancient ocean froze in place or simply cycled faster than the record can resolve, and paleoceanographers remain genuinely split on the question. Every El Niño recorded with modern instruments, going back to the 1950s, has ended within 1 to 2 years. The 3-million-year-old mud remains the only record of a Pacific that may not have kept that promise.